People refer to like all of the DeepSeek releases this week as kind of like DeepSeek is in the Matrix. Like people are so shocked that you can do these things that DeepSeek is releasing. And while the DeepSeek research is great, it's awesome. If you've been at the forefront of these things, you know that people are holding back. Even DeepSeek is holding back, and all of this is still holding back what is available. And the reason is like we have in the last few years been able to make so many advancements compared to where we were before that like even just like throwing you like super advanced stuff that is like half the research that I've been working on would still be like light years further than we are at the moment, right? But so um, let me outdo DeepSeek and let's move the dial further here. Let's stop holding this back. So this is 98% compression and it's lossless. And then this is, I've tested this all across the board on image-based datasets. I don't know how well it would perform on text, but outside of image or like, so like images, anything like and around image classification, you're going to get 98% compression and lossless compression, like guaranteed, right? So like, there's the Kaggle competition right now is like $40,000 for this for like a 30% compression, I think, and lossless. So here's 98% and lossless. I'll show you 100%. Like so, literally, like there's $40,000 rewards out for what I'm showing you here, and I'm smoking those $40,000 reward competitions. So this notebook presents a robust autoencoder-based compression pipeline for the Fashion MNIST dataset, incorporating a custom Moonshot encoding format for efficient storage and retrieval. The project aims to develop a fault-tolerant compression mechanism, ensuring data integrity and handling common issues such as NaN values, gradient instability, and buffer mismatches. Key features as to how this works: it's data loading and pre-processing from the Fashion MNIST dataset. Then I have my autoencoder model. So it's a deep feed-forward autoencoder with layer normalization, leaky ReLU, and a dropout. I also implement gradient clipping and low learning rate. I've reduced learning rate significantly over time. That's how I've been able to do it. And it encodes images into a latent space of configurable dimensionality. And then, so that's very important, right? So I'm using high dimensional space in this instance, but the major thing is that I define and purely upfront all of the dimensions of the hyperdimensional space, right? The image problem with hyperdimensional space, if you use like a point care ball, for example, or anything like that, is that you get massively exploding gradients around the edges. Like the closer that you get to the edge, the less you can actually measure distance. And then you want the model to push data towards those edges though. And then so that creates problems. And then so mathematically, I've found ways around that, and essentially I just define the space entirely, right? So then I define the exact space, and it's not a point care ball, and then that allows me to essentially avoid that problem of like exploding edges, and so I can still push data to the edges, and it doesn't explode out, plain and simple. And then I use my Moonshot encoding format, which is a custom binary format. It's all MIT licensed for storing compressed vectors. And then I utilize within this a magic identifier, versioning and encoding method, dimensionality and sample count, and compression ratio, and CRC32 sum check. Essentially, you can look through all the code here. It's all MIT licensed as to how exactly I'm able to do this, compress this, create the hypervectors, etc. It's a lot of code with regards towards the hypervectors themselves, the compression mechanisms, how exactly they work, etc. And then so we go through and I train epochs, and then I can tell up front that it's going to be successful, right? Because my first training loss is 0.19, which is well below 1, which is where I would want it to be, right? Like if it was like 0.9 or 1.0, I would be happy, but it's 0.19. Like that's very significant. It ends at 0.10, which is like near lossless with regards towards what the model's picking up. And then we can see that's exactly what happens. Compression ratio. So the original data size is 180 megabytes. If you were to store my hypervectors, you would be storing 2.29 megabytes. You could almost store the entire Fashion MNIST data set on a singular floppy. That is a compression rate of 78.4x times, or 98.72%, almost 99% compression. And then, as you can see, reconstruction error, 0.000 all the way across the board. And then here's our beautiful, beautiful, beautiful visualization of the data. If you're familiar with the Fashion MNIST data set, it's like people are struggling to do this. there's very clearly problems within the Fashion MNIST dataset. It misclassifies some of the data flat out. Like some of it's mislabeled, and then so your typical model, like that's the reason why the models struggle with that. And then so utilizing not the labels themselves, but abstractions of the data, as I've gone through and told you before, and other methods that I've open source released at this point. Here it is, all MIT licensed, available for you to do whatever you would like with. Please. And if you like this type of content, please like and subscribe. Thank you very much.